Okay. So this is a Zoom meeting for Physics 231C. We're finishing this week and Monday, chapter 4 of the textbook. So we've already finished chapters 1, 2, and 3. 1, 2, and 3 are really just on math. Chapter 4 is where we start to study physics, because chapter 4 concerns forces, not just describing motion, like in chapters 2 and 3, but how do physical forces and interactions affect motion? And the answer is given by Isaac Newton's 3 laws of motion. So that's the subject of chapter 4. Now, since this is where we start to study physics, this is a kind of a more difficult chapter than the chapters which were just on math. And now, after we finish chapter 4, that'll be next Monday. The next day, Tuesday, will be the first exam. So at the end of today's Zoom meeting, I'll talk a little bit about what will be on the exam. And today we'll go over some examples, problems from chapter 4 to see how to do calculations of the kind that are in the homework assignment and that will be on the exam. Chapter 4 is really the most difficult chapter in the book because this is where we start to learn physics. And we have various things to learn in this chapter. First of all, what are force and mass? What is a force? What are some examples of forces? What's mass? What is mass anyway? And then what are Newton's 3 laws of motion, which rely on the concepts of force and mass? In particular, there's Newton's second law, which is an equation. It's the equation of motion when force is involved. It relates the net force on an object to the acceleration. Now, we've already studied acceleration in the previous chapters. Acceleration is the change of motion. You know, strictly speaking, acceleration is the rate of change of velocity. But in other words, if velocity is changing, then there's acceleration. And that acceleration is related to the net force acting on an object. In most problems, there are numerous forces acting on an object. There could just be one force acting on an object, but that would be a little unusual. Usually, there are several forces involved. So you have to know how to get the net force or the total force. That's related to the acceleration. Now, in chapter 4, there's a section that describes several different kinds of force. For example, friction, contact between objects. When objects are in contact, they exert forces on each other. And we usually separate the contact force into 2 parts. The normal force, which is perpendicular to the surface, where the surfaces where the 2 objects are in contact, That's the normal force. And then the other direction, the tangential force, that's usually called friction. Another example is tension. That's when you have a cord, a string, or a cable connected to some object. Well, the cord will exert a force on the object. What is a force? Well, the simplest answer, the answer you probably learned back in grade school, is force is a push or a pull. Not quite that simple. The contact force, the normal force, is a push. Tension force, the force exerted by a string which is tied to an object, that's a pull. You know, if I tie something to a mass, I can pull it. I can't push it. You can't push something with a string. You can only pull it. Friction, is friction a push or a pull? Well, I'm not quite sure. So to say a force is a push or a pull is a little bit of an oversimplification. What about the force of gravity? You know, the Earth is exerting a gravitational force on the moon, but they're not in contact. They're many thousands of miles apart. So it's not exactly a contact force. In fact, that's what we might call a field force, the force exerted by the gravitational field. In the case of gravity, we sometimes just call it an action at a distance. When we come to electricity and magnetism, the forces of electricity and the force of magnetism, which is not for physics 231, that's for physics 232. Well, those are field forces. In other words, electricity is a force field, and magnetism is the effect of a force field. There's also a section in this chapter on the role of force in circular motion when an object is moving around a circle. We already studied circular motion back in chapter 3. So we already know there's a centripetal acceleration. Well, then what force is related to that acceleration? You need to take notes when you read chapter 4, because you're going to need the equations that you'll find there to do the homework, and you'll need the equations to do the exam. So take notes when you read chapter 4. The best way to study for the exam is to study the notes you took. You don't want to go back and reread the chapter again. So take notes when you read the chapter, and then to study for the exam, study your notes. Let's see, somebody asked a question on the meeting. For acceleration due to gravity, should we use 9.8 or 9.81? 9.81. 9.8 is pretty close to 9.81. So it probably doesn't matter if you use 9.8 or 9.81. But, 9.8 has 2 significant figures. 9.81 has 3 significant figures. Averaged over the surface of the Earth, the acceleration due to gravity is a little closer to 9.81 than 9.80, although it can be higher or lower than that. But I would say that in most problems, 9.8 will work, but use 9.81. As long as you're doing a calculation with your calculator, you can easily do the calculation with 3 significant figures. So take notes when you read the chapter. Section 4.1 is called force and mass. And when you study section 1, you should be able to answer the question, what is force? And also, what is mass? Force is a push or a pull, but it's not quite that simple. Force is when two objects act on each other in some physical way. Like if they're in contact, they're pushing on each other. Or if one is a rope tied to another object, then the rope may be pulling the other object if the rope is under tension, and so on. We're going to see other examples of force later in the semester. For example, the force exerted by a spring or the gravitational force. We already know a little bit about gravity, the gravity near the surface of the Earth. But what about gravity in space? Or what about the gravitational force on the moon? Or for that matter, what about the gravitational force on the Earth? There's a force exerted by the sun. There's also a force exerted by the moon. Those forces produce tides, the ocean tides. So, what is force? Well, it's when objects interact. In order to have a force, you have to have two things. You have to have two objects. One object exerts the force. The other object experiences the force. But then Newton's third law says, at the same time, the second object will exert the force, and the first object will experience the force. So in fact, forces always appear when objects interact with each other, and there are forces on both objects. Now, what's mass? Well, mass, it's sort of, if you've taken a course in chemistry or if you've done a chemistry lab, you measure mass with a scale. It's some number of grams. Well, the chemists use grams as the unit of force. Physicists use kilograms. So the standard unit of mass is the kilogram. It's sort of a measure of the amount of a material, but what amount is it? I mean, what amount are you talking about? And the answer is, it's the numerical measure of inertia. Inertia is a tendency of matter. Matter has a tendency to remain in motion with constant velocity. And that's called the law of inertia. That was first stated by the great Galileo. And the higher the mass, the greater this tendency. Mass, you can think of, probably the best way to think of mass is the resistance to change. It resists change in velocity. So that's section 1. Then section 2 is Newton's laws of motion. And there are 3 laws of motion: the first law, second law, third law. They look pretty simple, but the looks can be deceiving. They're not as simple as they look. That's why it took a great genius like Isaac Newton to figure them out. The first law says, if the net force on an object, and so here again, we're going to have to know what is meant by net force. If the net force on an object is 0, then the object moves with constant velocity. So, for example, if there's no force acting on an object, it'll just move with constant velocity. Now, that may seem simple enough. I mean, an object at rest stays at rest. Everybody would believe that. an object in motion remains in motion. Everybody would believe that, but not everybody would believe that, because Aristotle said that the natural state of motion of a mass is to be at rest. So if an object is moving, it'll slow down and come to rest. That's what Aristotle taught. It's wrong. If there's no force acting on an object, it'll just move forever. That's sometimes called the law of inertia. It was first stated by Galileo, and Newton made it his first law of motion. Then Newton's second law says, what if there is a force acting on an object? If the net force on an object is zero, then there's a constant velocity. The object just moves. It just moves freely. It doesn't slow down. It doesn't speed up. It doesn't change its direction. It just moves in a straight line. But what if there is a force? Then its velocity changes, and we know the change in velocity is acceleration. So in particular, the acceleration vector is equal to the force vector divided by the mass. And what's the mass? Well, the mass is the amount of material. The mass is the amount of resistance to change. For a given force, if the mass is larger, the acceleration will be smaller. If there's a larger resistance to change, then the amount of change will be less. So acceleration goes like 1 over mass. And that's Newton's second law. Physicists usually call that the law of motion. And we know from chapter 3 that acceleration and velocity are vectors. Force has to be a vector. Really, it's this equation, Newton's second law, which defines what is a mass and what is a force. Then there's Newton's third law. It's not really a law of motion. It's a law of interactions. It's a law about forces. But since forces affect motion, we call it the third law of motion. Now, this is something that everybody knows and almost nobody understands. Everybody knows that for every action, there's an equal but opposite reaction. But not very many people really know what that means. Most people have a wrong idea about what that means. You know, you say, well, if I'm hit by a car, then I'll fall down. So for every action, the car hitting me, there's a reaction. I fall down to the ground. Well, that may be a true statement, but it has nothing to do with Newton's third law. And that's the way most people kind of see this idea of action and reaction. They sort of think that first the action happens, and then later there's a reaction. Something happens. That's not what Newton's third law means. The action and the reaction occurs simultaneously. You know, if I'm hit by a car, the car exerts a force on me. And Newton's third law says, I exert a force on the car of an equal strength. Or don't take it to be a car, take it to be a Mack truck. If I'm hit by a Mack truck, well, I'm not likely to be hit by a Mack truck, but suppose I'm driving a Volkswagen and the Mack truck hits the Volkswagen. Well, obviously the Mack truck is going to exert a force on the Volkswagen. And the Volkswagen is going to exert a force on the Mack truck. And the strength of these two strengths are equal. Seems very hard to believe. That's why hardly anybody really understands what's meant by Newton's third law. Unless you take a course on physics, you probably won't understand the meaning of action and reaction. The word action was used by Newton. Well, what did he mean by action? That's kind of an archaic word. Nowadays, we call that force. So really, a more modern statement of the third law would be, for every force, there's an equal but opposite other force. Or to say it better, when two objects interact, there are two forces, and they're equal but opposite. So, if I have two objects, let's say it's the force of gravity. So here's the Earth, and here's the moon. Well, the moon is pulled towards the Earth by gravity. And the Earth is pulled towards the moon by gravity. So when the Earth and the moon interact gravitationally through the gravitational field, there are two forces. There's a force on the moon, there's a force on the Earth, and these have equal strength, but opposite directions. All right, so in the reading quiz, there were a bunch of questions where you had to apply the ideas of Newton's first, second, and third law. Most people have already finished the reading quiz, but the reading quiz is due at the end of today. And that, the second part of that was questions about the concepts of Newton's three laws. A lot of people have already finished it. Some people are still working on it. Now, section 3 describes different kinds of forces. For example, there are contact forces. When objects are in contact, there are equal but opposite forces at the surfaces. So here's an example. A block is resting on a ramp. Let's say it's not moving, it's just sitting there at rest on the ramp. You can picture that. There are forces on the block. There are forces on the ramp. It's a contact force. And if this ramp is on the surface of the Earth, there's another force on the block. Besides these two, there's gravity. So there's the force of the Earth pulling the block down. The Earth also pulls the ramp down. Maybe the ramp is sitting on a floor. Well, then there's a contact force between the ramp and the floor. So there are all kinds of forces going on. But if we just concentrate on one force, or on one object, I should say, namely the block, there are three forces acting on the block. There's normal force. That's a force, that's a push. That's a force pointing away from the surface and perpendicular to the surface. And there's a tangential force, that's called friction. And there's a gravitational force, which of course points towards the center of the Earth. And those are the forces acting on the block. And if the block is at rest, the sum total of those three forces is zero, because if there's a force, there's an acceleration. But if an object is just sitting there at rest, not moving, well, the acceleration is zero. So the force has to be zero. the net force. None of these forces would be zero, but the net force would be zero. The net force is just the sum of the three forces. Three arrows. And the section describes kinetic friction and static friction. So you have to know the difference between kinetic friction. Friction, if the block were sliding, the block could be sliding up the ramp. It could be sliding down the ramp, depending on how you set it on there. Or it could be not moving on the ramp. It could be static friction. So be sure you read about kinetic friction and static friction. There's tension. When a cord under tension is connected to an object, the force is called T for tension. Of course, force has to have a direction. The direction is parallel to the cord, because a cord can pull on something, but it can't push something, or it can't swing something to the side. It just pulls. So the direction of the force is parallel to the cord. They discuss drag, which is kind of like a frictional force. It's friction between a moving object and the air through which it's moving. You know, in order to have a force, you have to have two objects. One object to experience the force, one object to exert the force. If an object is moving through the air, it's in contact with the air, or the air molecules. Those are exerting a force on the object. And of course, by Newton's third law, the object is exerting forces on those molecules. So drag is an example in aerodynamics. It's usually called air resistance. Or if you had something moving through water, you could have water resistance. Because as the object moves through water, think of a boat moving through the water, it's pushing the water out of the way. Well, push is a force. And of course, the water, by Newton's third law, is pushing back on the boat. So if you set a boat in motion and the motor goes out, it'll eventually come to rest. Not because it doesn't have any inertia, but because there are forces acting on it. And so Newton's second law causes it to slow down and stop. Gravity we've discussed before at the Earth's surface. At the Earth's surface, we have the universal or the common acceleration due to gravity, 9.81 meters per second squared. In space, we have a formula for gravity. And gravity goes like 1 over the distance squared. That was Newton's theory of gravity. NASA relies on that for all of their space satellites. And then finally, read section 5 about the forces that occur in uniform circular motion. If an object is moving in a circle, it has an acceleration, even if its speed is constant. Speed could be increasing, but it doesn't have to be increasing. Think of a race car going around a circular track at a constant 60 miles an hour. It has a constant speed, but it has a changing velocity because the velocity is always tangent to the racetrack. So it's changing as it moves around the racetrack. Well, change in velocity is acceleration. So there has to be acceleration. Yeah, there's centripetal acceleration, which we studied back in chapter 3. Acceleration is v squared over r. That's the centripetal acceleration. So that's the acceleration in the radial direction. But it's towards the center. So it's actually negative v squared over r. If I take the radial direction to be away from the center, the acceleration is towards the center. Well, if it has that acceleration, it has to have a force. Now, of course, a force is a vector, so it has a radial component. It'll be the mass times the centripetal acceleration. And there are many different kinds of forces that could produce circular motion. For example, as the moon revolves around the Earth, there's a force of gravity where the moon is pulled towards the center of the Earth. That's the centripetal force. Or if you have a ball on a string and you're whirling it around, there has to be, you're whirling it around, well, that's moving on a circle because the length of the string is constant. So that's the radius of the circle. And there must be a force pulling the ball towards your hand, which is the center of the circle. And yeah, there is a force. It's the tension force of the string that's attached to the ball. If the string should break, the ball would no longer move in a circle. It would just go off in a straight line. All right, so we're going to go over some examples. So these will be sort of hints for some of the homework. So we'll go over some homework hints. I have them over here, actually. This Zoom meeting is going to be too long if I go over everything, so I'm going to skip some things. One example is the Atwood machine, this problem. It's in the assignment. I'm going to skip that. Here's all the hints that you need, and these notes are available in the supplemental content. So if you want to look at this more carefully, look up Zoom notes at the supplemental content, and these hints will be in the notes. Here you have two objects. So you have to analyze the forces and the net force and the acceleration of two objects. And then use algebra to calculate the unknown quantity. Or here's another example, an icy slope. You have, let's say, a car on an icy slope, and it's sliding down the icy slope because there's not enough friction between the tires and the ice. How fast will it move? Or what acceleration will it have? Well, you have to analyze the forces. You have to know that the coefficient of kinetic friction is some value mu. You have to write down Newton's second law. There are actually three different forces to combine. And then you have to apply algebra to solve for the unknown. So again, these notes are available in the supplemental content, but I'm going to skip it today. Let's consider this problem, which is like one of the problems on the exam. On the homework. You have a block tied to another block by a cord, which goes over a pulley. And this block is on a ramp, and there's friction between this block and the ramp. And this block is just moving, vertically. It's tied to the cord. So here is the crucial method for doing problems with Newton's second law. You have to draw force diagrams. So learn how to draw force diagrams. It's in chapter 4. It's called tactic number 1. Tactic number 1, which you read about when you read the chapter, is how you do calculations with Newton's second law. You draw a force diagram. So this block has two forces acting on it. the force of gravity pulling it down, and the tension of the cord pulling it up. And this block has 4 forces acting on it. There's the force of gravity pulling it down. There's the normal force exerted by the ramp, pushing it perpendicular to the surface. So we could call that N for normal. There's the tension of the cord. And when a cord goes over a pulley, the tension remains constant. So the tension is the same on both sides of the pulley. So this tension is the same as this tension. And the other force is friction, which acts in the opposite direction from the velocity. Now, you got these 2 force diagrams. You'll have to have 4 equations. You'll have to have Newton's second law in the different directions. So, for example, for this object, the mass times the acceleration is, let's calculate the downward acceleration, is mg minus t. And for this object, the mass times the acceleration is, let's take the acceleration to be up. So this is falling down, this is going up. The force in the upward, up the ramp direction is T minus F, minus the component of the gravitational force in the direction parallel to the surface. The gravitational force is downward, but that can be separated into a parallel component and a normal component. So the parallel component will contribute to M1A, the acceleration of the block up the incline. T will be positive up the incline. F will be negative down the incline. Gravity will be down the incline. It'll be M1G sine theta. The sine theta is there because I have to project out the direction parallel to the surface. There's also a force perpendicular to the surface. That would be N minus M1G cosine theta, but there's no acceleration perpendicular to the surface because the block just moves on the surface. So N minus M1G cosine theta will be 0. And there's a relation between F and N. F is the coefficient of friction, kinetic friction, times N. So you have these 4 equations. You want to solve for something. It depends on what the problem is asking you to solve for. The problem will give you some information and ask you to solve for some unknown. Well, you have to use these 4 equations together. And you've done that at algebra, solving simultaneous equations. For example, you could combine these 2 equations to eliminate the tension and get an equation for the acceleration. So if the other quantities are given, you can calculate the acceleration in that way. So force diagrams, that's something you need to understand. You have Newton's second law. It says the acceleration is the net force divided by m. And acceleration of force are vectors. So you have to be able to calculate these vectors. And in particular, the net force is a sum of multiple vectors. So you have to know what are the vectors that are acting and producing the net force. Suppose we have a block resting on a ramp at rest. It's not moving. It's just sitting there. You can picture that. Well, why doesn't it slide down? Well, it doesn't slide down because there's friction. There's a tangential force, frictional force, which holds it up. So you would draw a picture, a force diagram. You would draw the object, in this case, this block, and all the forces acting on it. You don't put anything on the force diagram except the forces. You don't put on the acceleration vector, you don't put on the velocity vector, you just put on the force vectors. There's a contact force, which has a component perpendicular to the surface. We'll call that the normal force. There's a frictional force, which is pushing it up the ramp. It's not moving up the ramp, it's at rest, but it's got a force on it acting up the ramp. Then there's a gravitational force pulling it down. And I can separate that into a component normal to the surface and tangential to the surface. The tangential component will be down the surface. So again, by a little bit of trigonometry, the length of the gravitational force is just the weight. The weight is the mass times the acceleration. Acceleration due to gravity, g, 9.81 meters per second squared. Well, the component perpendicular to the surface, see this angle theta, which is the same as this angle theta by high school geometry. The component adjacent to theta has a projection cosine theta. Cosine theta is the adjacent over the hypotenuse. The hypotenuse is mg. So the force perpendicular to the surface is mg cosine theta. And the force parallel to the surface, actually downward, will be mg sine theta. Now, if this is at rest, then the net force is zero. So you have the perpendicular component, n minus mg cosine theta, has to be zero. And you have the parallel component, f minus mg sine theta, has to be zero. Acceleration is zero. So these forces add up to zero. This is the net force perpendicular to the surface. This is the net force parallel to the surface. You also know F is mu n, where in this case you have the coefficient of static friction because the block is not moving. And the coefficient of static friction says that the frictional force must be less than the normal force times the coefficient of static friction. So if you put these various equations together, you'll find that in order for the block to stay there and not slide down, the tangent of theta must be small enough. It must be smaller than the coefficient of static friction. I'm going to run out of time. So let me just say that here's an example. Pulling a block, say this is the tension in a rope or something, at an angle. Well, you make a force diagram for the block. It'll have that force, the tension force from whoever's pulling it, a normal force, a gravitational force, and a frictional force tangent to the surface being the floor. So you have a horizontal component, MAX, X would be in the horizontal direction, is F cosine theta, that's the horizontal component of the tension force, minus F, the frictional force. And you have a vertical component where the acceleration is zero because the block is not going off of the surface, it's just sliding along the surface. So, you know, it's always the same. You draw a force diagram. Before you do anything else, you draw a force diagram. And you put all the forces and nothing else on the force diagram. Then you write Newton's second law, perhaps separated into different components. And then it's algebra. There are some problems where there's more than one object moving. So here's a problem where you have someone pushing with a force F on a block M1, and there's another block M2 in contact with M1. So how would you analyze the acceleration and the forces? Well, first step is to draw force diagrams. Here's the force diagram for M1. There's a force directed to the right, which is exerted by the person pushing on M1. And there's a force directed to the left, which is M2 pushing back on M1. So that's the force diagram for M1. And the force diagram for M2, well, the only force on M2, I'm only analyzing the horizontal forces because the vertical forces are sort of irrelevant since these two masses won't move vertically. What's the horizontal force on M2? Well, it's the contact force exerted by M1. So the force on M2 is F21, force acting on 2 exerted by 1. And this contact force is F12, the force on 1 exerted by 2. And if I call this force F sub I, then this force is minus F sub I by Newton's third law. So you have various equations. M1A is F minus Fi, just by looking at the force diagram. And M2A is Fi, just by looking at the force diagram. So those are Newton's second law. First, you draw the force diagrams so that you're able to write down Newton's second law. Mass times acceleration is net force. In this case, the net force is F minus Fi. In this case, the only force is Fi. They have the same acceleration because they're in contact. If they didn't have the same acceleration, they'd come apart. But they're just going to remain in contact. You can picture that. So you have these two equations. So you start with a picture, namely force diagrams. You write down the equations, then you apply algebra. Let's suppose your goal is to calculate, I don't know, with the acceleration. Well, you can't use this force, this equation, to determine the acceleration because you don't know what Fi is. And you can't use this equation to determine the acceleration because you don't know what Fi is. You have two equations with two unknowns. The two unknowns are A and Fi. So you've solved problems like this in your algebra classes, two equations with two unknowns. You substitute one of the equations into the other one. So let's start with this equation. M1A is F minus Fi, but let's substitute for Fi M2A, because that has to also be true. And now if I move all the accelerations to the left-hand side, divide through by M1 plus M2, I can find what the acceleration is. It's F over M1 plus F2, where F is the force of the person pushing on block M1. And the other part of the problem might be, what's Fi? Calculate Fi. Well, if I know what the acceleration is, I can calculate Fi by just using this equation. So, you have to use algebra when you have more than one object in motion. And you notice I've never used a calculator. It's only when you finish the algebra that you know how to use your calculator. Here's a problem which is on the assignment called falling and pulling. You have a block on a table. There's a pulley. There's a block connected to the first block by a cord or a rope. The second block will accelerate downward. The first block will accelerate to the right. The two acceleration magnitudes will be equal because they're tied together. So if this one moves down by 1 inch, this will move to the right by 1 inch. So they'll have the same accelerate. They'll have the same velocity. They'll also have the same acceleration, the same change in velocity. So to analyze the problem, you draw force diagrams. Here's the force diagram for this mass if there's no friction. It's just pulled by the tension in the cord. And here's the force diagram for this mass. It's pulled up by the tension in the cord. It's pulled down by gravity. So now here are the equations. M1A is equal to T. And here's this equation. M2A, we take A downward, is M2G minus T. So again, we have two equations for two unknowns. The two unknowns are A and T if we're told the masses. If we're told what the masses are, then the unknowns are A and T. So you can solve those two equations. One will, combining them, you'll be able to calculate A and T. And now you need your calculator because you're going to have expressions here. This expression will have to be evaluated for the numbers you know, namely the masses. And for that, you'll want to use a calculator. Block pulled at an angle. That's one of the problems. That's like this problem on the homework assignment. So the two blocks in contact is on the assignment. The falling and pulling is on the assignment. Pulling a crate at an angle, that's also on an assignment. We sort of already did this, although I went over it quickly. The force diagram looks like this. We make a force diagram for this moving object. There are four forces. There's the force of the rope. Here's the rope, the tension on the rope that's pulling it. And that's at some angle, called the angle theta with respect to the horizontal. There's the normal force perpendicular to the surface, perpendicular to the floor. So that's upward. There's the gravitational force, mg, pulling it down towards the earth. That's the weight. And there's friction, because it says in the problem that there's a coefficient of friction here, so there's friction. So you have four. So here's the force diagram. Four forces. And now you have to calculate the net force. You have to add these four vectors. Well, we'll separate it into a y component, which is vertical. The y component will be n, which is upward, f sine theta, which is upward, minus mg. And that's the mass times the vertical acceleration. Of course, the vertical acceleration is zero because the crate is just going to move along the floor. It's not going to be pulled up off the floor. Then there's the net horizontal force. Well, this tension has a horizontal component T or F cosine theta. And then in the other direction, there's the frictional force minus F. And that has to be m times the acceleration in the x direction. We could just call that ma. Since ay is zero, we might as well just call ax equal to a. So that's Newton's second law. We could only get those equations by looking at the force diagram. That's why in all these problems, the first step is to draw the force diagram. And now we take these equations and use algebra. Say we want to calculate the acceleration. Well, then MA is F cosine theta minus F. And F is mu n, where this would be something sliding, so this would be the coefficient of kinetic friction. And n I know from this equation. So I can say MA is F cosine theta minus mu n. And n, since this quantity has to be 0, n is mg minus F sine theta. Now the acceleration will be constant. And I guess the problem probably asks something about how far did it move? Well, you have to think back to chapter 2. We learned that constant acceleration, the distance is 1/2 at squared. So again, I'm going over this pretty fast, but if you want to have a little more time to ponder this, it's in the Zoom notes in the supplementary content. Here's two masses on an incline. Already talked about that. Here's pulling and sliding with friction. Already talked about that. So, you can look these up on the supplementary content. Now, I want to make sure I have enough time to talk about exam 1. So this problem set 3 is due Monday, September 25th. Then exam 1 is Tuesday, September 26th. You should look up the README files for exam 1. And there's also a practice exam for exam 1. So on Lon Kappa, read the information files about the exam and use the practice exam to practice doing problems. The exam will be 70 minutes long. It'll be open from 7 p.m. to 10 p.m. Tuesday night. It'll be at lonkappa.msu.edu. It's 70 minutes long, and you can't take a break after you start the exam. After you start the exam, a timer will start. You have 70 minutes from when you look at the first question to when the timer turns you off. Be sure you have trustworthy internet access, and be sure your laptop is charged. If your laptop only has 40 minutes of charge, you might not be able to get the whole 70 minutes to work on the exam. So make sure you have, and you have to make sure you have trustworthy internet access. I guess in the dorms, the internet access is pretty trustworthy. But if you're in a apartment, you might have kind of flaky internet access. You might be better off not doing the exam in your apartment where the internet access might fail and you wouldn't have the full 70 minutes to do the exam. You might try to take the exam in a building on a campus, like the STEM building. You could go to the STEM building. The internet access in the STEM building is, the Wi-Fi access is dependable there. So you might want to go to the STEM building as a place to do the exam, or maybe the library. You can use a help sheet during the exam. It should be 1 page, 2-sided, handwritten, and it should be equations mainly from the 3 chapters that'll be on the exam, 2, 3, and 4. Here are things you need to know for the exam. From chapter 2, the equations for constant acceleration, how to do calculations for free fall, where the acceleration, that's the acceleration in the vertical direction. Y is negative g. Chapter 3 there were two important examples in chapter 3 of motion in two dimensions, namely projectile motion. You did a bunch of problems for the homework on chapter 3 involving projectiles, and uniform circular motion with the centripetal acceleration. So you should expect to see some problems, at least one problem on projectile motion, maybe one problem on circular motion. You need to have the equations for those problems. You remember projectile motion had 3 equations. Well, you have to have those written down on your help sheet. And then chapter 4. So you have to understand the forces like contact forces, friction, tension, gravity. You'll have to use Newton's second law, where the force is the mass times the acceleration. Or if an object is at rest, so the acceleration is 0, that's called statics. Static situation, the net force is 0. Oh, and now this equation can be misleading because what force are you talking about? What force is equal to m times a? I mean, we saw problems a minute ago where there were multiple forces. So which force do you use? Well, you use the net force. Which is the vector sum of all the different forces that are acting. And don't forget gravity. And don't forget friction. And in order to solve problems with Newton's second law, the only way to do it is to start with force diagrams. Draw force diagrams. That's in chapter 4, tactic 4.1. Draw force diagrams, and you're going to get a lot of practice using force diagrams in the homework assignment, which is due Monday. Then you have the exam Tuesday. So make a help sheet and study your notes. You've been taking notes in a physics notebook throughout the semester while you're doing the problems, while you're reading the chapter. That's the best way to study for the exam, which you're going to get the next day. You've finished the chapter 4 assignment. You have a rather short time to prepare yourself for the exam. What's the best way to prepare yourself from the exam? Study your notes, because those should all be familiar to you since you wrote them. All right, now let's see if there are any questions. There's some questions on the chat. For acceleration due to gravity, should we use 9.8 or 9.81? Well, I would say use 9.81. For question 44, when I used 9.8, it said the answer was wrong. Well, yeah, use 9.81, try 9.8. Try 9.81 if 9.8 doesn't give you the right answer. Will you be able to go over part 2 of the optional car in a circular arc question? Yeah, I could. So those are the questions that are on the meeting chat. Are there any questions people would like to ask just orally? If you don't want to type it into the chat, you could just unmute your microphone and speak up. All right, somebody on the chat asked about a question about a car in a circular arc. It's one of the optional questions where it's just for practice. You don't actually get any points for doing it. Let's see if I can find it. So here's ln kappa. there are several of these optional problems for practice. You don't get any points for doing them. One of them is car on a circular track. So it's this. A car rounds a circular curve with radius r. From P to Q, the speed is constant. What's the acceleration vector at P? And now part B, suppose the driver presses the acceleration pedal at Q, the speed is then increasing at a rate a sub tau. That's tangent to the circle. What's the acceleration vector just after Q? So step one in every physics problem is to draw a picture. Now here we already have a picture, but it's not a very complete picture. You'd like a better picture. What else would you want to put on this picture? Let's see if I can find a place to draw. I'm not sure I have space to make a picture. Let's see if I can find a space. Yeah, here's a space, I guess. All right. So we have here an example of circular motion, but it's not uniform circular motion because the speed is not constant. So I would say the first thing to draw is a circle. Now, here's the point P here. And here's the point Q here. And this distance is the radius of the circle, so that's r. And this distance is also the radius of the circle. So that's also r. And this angle, you can see from the picture and the statement of the problem, that angle will be this direction. That's 45 degrees. So the angle there is 45 degrees. Now, part A is about the point P. Well, at the point P, the speed is constant. So at the point P, so this will be part A of the problem, there's a constant speed, v0, and so the acceleration is maybe it'd be better if I did it like this. The acceleration is v0 squared divided by r. Now, that's the magnitude of the acceleration. It's just the centripetal acceleration towards the center of the circle. So here's the center of the circle. If I want to write the vector, whoops, I lost it. Where was that? Car on a circular track. It looks like I got to write two components. So let's do the x and y components. So let's do it this way. A sub x is negative v0 squared over r. And a sub y is this direction, x is this direction. A sub y is 0. So A is in the minus I hat direction. It's v0 squared over r. That's the magnitude. It's in the minus, the acceleration here is in this direction. I can't draw here, but the acceleration here at the point P, the acceleration is in the negative x direction. It's towards the center of the circle. Now, part B, so for part B, is at Q. Now here, there's a tangential acceleration because speed is increasing. So this is not uniform circular motion. Here, the speed is increasing. So let's see what the acceleration vector would be. The acceleration vector will be minus v squared over r in the r hat direction plus a sub tau in the angular direction. So again, this is the acceleration vector. This is the r hat component. And this is the tangential direction. Now, how fast is it moving when it reaches Q? Well, the driver applies the accelerator pedal at Q. So at Q, it's still moving with a velocity v0. But now it's accelerating, so now it has a tangential component of acceleration. Now, what's AX? Well, r hat is in this direction. T hat is in this direction. So r hat has an x component and a y component. And t hat also has an x hat component and a y hat component. So if I want to know a x, it'll be minus v0 squared divided by r. And now the r hat part, the x direction, sorry, the x part, the x component of r hat is 1 over the square root of 2. So, here's r hat. And here's t hat. And now r has an x component, which is the unit vector has length 1, which is just 1 cosine of 45 degrees. Cosine of 45 degrees is 1 over the square root of 2. But now there's another part here, which has to do with a sub t. Now t has a x part, an x component, which is in a minus x direction. So it'll actually be minus a hat t over the square root of 2. And that goes in this box. And then there's also ay, which similarly r hat has a y component, a plus y component. But don't forget that minus sign. And t hat has a plus y component. In both cases, it's r hat sine 45, but that's r hat over the square, but that's 1 over the square root of 2. This is t hat cosine 45 degrees, but that's also 1 over the square root of 2. So ay is similar to that. I don't know if this is a problem in the book. There seem to be a lot of questions about the problem. Well, not so many, but there are a few questions on the discussion board, so you can read about the you can read the questions and answers on the discussion board. That may help you. All right. Well, I haven't stopped the recording yet, so let me stop the recording now. Let's see. How do I stop the recording?